Welcome to Lecture 8 in our second semester class on stochastic processes. The aim of today's lecture is to present the Bismut derivative formula for the second order derivative of the heat semigroup of the semigroup induced from solutions to stochastic differential equations. And the ultimate result in our particular case of a one-dimensional SDE with additive noise, so sigma being the identity matrix, and with a smooth vector field B, reads as follows. Let PT be the Feller semigroup which is associated to solutions of our stochastic differential equation in one dimension, where the sigma is confined to be identity and B is in this case, C2 smooth function or vector field. And let Q and R be solutions to the following ordinary differential equations with random data. Qs is the object that we already all know from the first order Bismut derivative formula. Qs solves the equation Q dot S equals plus minus Qs B prime of xs ds, and it starts at the unit in 0. And R is the solution to the differential equation that R dot S equals Rs B prime of xs minus Q s squared times b double prime of xs, which is supposed to start at 0. So here in the equation or the ODE for R, which defines the R, we have the Q function appearing where the Q is the solution to this ODE for the first order derivative that we had already seen. Then let t be a fixed positive time and choose two control functions, as we would call them, namely two functions which are deterministic, probably, which are defined on the interval from 0 to t, which are chosen such that both functions vanish at terminal time, at this time capital T, which is a time of our choosing. Let us furthermore assume that this L function is constant 1 on a certain subinterval from 0 to s, where s is a certain time between 0 and t. And let us assume that the k function is identically 0 on the complementary subinterval from s to t. Then for any function in our function space, of functions which are continuous and vanish at infinity, the heat semigroup or the semigroup induced from that solutions applied to the function f, that is a function which is twice differentiable. And if we evaluate that, or if we ask for the value of that second order derivative of the heat semigroup operation in a position x, then this allows a representation as follows. It's an expected value which involves certain stochastic integrals and the evaluation of the process of the function at initial time. Namely, we have two components. One is a component which is reminiscent of the formula that we already have for the first order derivative. It's phi of x t multiplied with a stochastic integral, which involves, but this in this case, the r function with the k dot function, which then in the product are integrated against the Brownian signal as a stochastic integral. And then there is a second component or a second expected value, which also involves the evaluation of the function phi at initial time. And the product of two stochastic integrals, which are integrals where the q function in both cases is multiplied with the derivatives of the L and the k control functions, and both are then ultimately integrated against the Brownian signal, and the product of these two random variables is then integrated, or is then taken into the product with the phi evaluation at that time, and then we take the expected value of this. So in this formula, the phi not, of course, there's a little bit of misprint, it's just the f, our function that we're dealing with, so it's just the f function. And what we see from this formula, okay, why is this formula significant? Again, it is significant because it represents this second order derivative, which is ultimately a derivative perturbation with respect to the initial position. It represents this second order derivative as an expectation which involves nothing from the function f except its actual evaluation, no derivatives or whatsoever, although this deals with the second derivative on the left-hand side. So therefore it's a significant formula, and it will allow us to derive all kinds of estimates on these second-order derivatives, which then, as I just said, will be a priori estimates in the end, because they do not take any significant use of higher-order derivatives of the function f. I will guide you now through the details of this proof for this formula. We will be doing pretty much a similar thing as for the first-order derivative formula, but computations will be more involved. I will give you all the necessary steps to take, and from that you will be able to do all the details on your own if you sit down and do the computations carefully. Okay, so we start in a similar fashion just by considering first the case when we are dealing with a smooth function, which is now arbitrarily smooth, if you like, and which solves again as before our basic PDE, a parabolic PDE that we already considered also for the first order derivative. Now we can take the spatial derivative of this parabolic PDE on both sides, which produces this version of a parabolic PDE, where now the first order derivative appears on the left-hand side, or the first order derivative, the combined first order derivatives in space and in time, and the maximal degree of differentiation you have on the right-hand side will be the third order derivative in space. As a consequence, this was the parabolic PDE, which we also considered already for the first order derivative formula. And we iterate this thing and produce or hit this parabolic PDE even with one more spatial derivative, which produces this formula, where again this L operator appears, but now acting on the second order derivative with respect to the spatial variable. So we will work with all these three partial differential equations in order to produce martingales. Now, as above, we will consider the Q function, which is the solution of an ODE with random coefficients. That's the same ODE that was appearing already in the previous argument. This is this exponential growth type PDE, which where the growth factor or the growth coefficient is obtained by computing the derivative of the B function along the solution trajectories of the x of the solution of the stochastic differential equation. And as long as it is not really important, I shall in the sequel omit this superscript x, which stands for the initial position of the solution of the stochastic differential equation. Unless I state otherwise, I shall consider the case when the starting position of that ordinary stochastic differential equation is fixed. And now we will have also another ordinary differential equation, which comes from this fact that we're dealing with second order derivative formula, namely we have another R process, as we call it. R is the solution to the following stochastic ordinary differential equation. R dot equals Rs times B prime of xs minus Qs squared B double prime of xs, and we start the R process at initial time at position 0. These are nicely behaved ordinary differential equations, so we want to assume, and we can in fact, that by the smoothness of the vector field B, that these are nicely behaved and controlled solutions to ordinary differential equations. Now we come back to our parabolic PDE and the function phi, and we will now we will construct several martingales, which we combine in the end for a big martingale, of which we then take the expectation and compare the expectations at different time points. So in that systematic approach, the argument that we are about to make will be pretty similar to the argument that we did for the first order representation formula. So the aim is now to produce martingales which involve these second order derivative formulas at the right moment of time, combined with the right quantities, such that in the end the corresponding magic formula appears. And as in the case of the first order derivative formula, there will always be the trick that we play a little bit of a game with forward and backward time reparameterization. So we typically will evaluate the function phi and its derivatives with regards to the time parameter in reflected time. So we fix a terminal time point, capital T, which is positive, and using the solution process X and these two solutions of the ordinary differential equations with random data and the function phi, our solution to the parabolic PDE, together with its first and second order derivatives, but in inverted time parameterization, we will now construct martingales. So here, our first martingale that we want to consider is the second order derivative in space of the phi function evaluated at time capital T minus t, where now the little t is the running time parameter. This will be evaluated at spatial position xt multiplied with the q process squared, and I add to this the first order derivative of the phi function evaluated again at this inverted time and in the spatial position again at the location of the solution process, and this will be altogether multiplied with this R function. And the claim is now that this real valued process is a local martingale. This will be shown by an application of Ito's formula, of course, and for simplified notation we shall write in the sequel that two processes are identified, are equal, modulo martingales, if in fact the two processes differ only by another process which is a martingale. So we write x equals y modulo martingales if they in fact do differ only by a martingale process. And since we are for the most of the time interested in martingale properties only, or deviations from martingales, we shall work with this concept of equality of processes. Okay, and also to simplify notation, we will typically write a b instead of a b of xs whenever we do computations below, and also we write phi of t minus t, or phi double prime or prime of t minus t, instead of the more complete notation phi t minus t evaluated at the position xt. So in other words, when there is no there is no risk of confusion, we shall omit the explicit dependence of the x process whenever this is appropriate. Okay, let's convince ourselves that this n process that we have just introduced is at least a local martingale. This n process is a sum of two summons, and we will expand each of these two summons by means of the Ito formula, and we will hope that all those parts which are not martingale components in the Ito expansion, that these two parts, or these two, if you like, trash parts or dirt parts, that they cancel one another from these two summons. So let's consider the first summand of this n process and do an expansion by means of by the Ito formula. So what do we have here? So here we have this, if we look at this process, we have of course a product of two processes, one of which is a process of bounded variation, and the other one is a process which involves the evaluation of the x process on a certain function. So that will be a situation where we want to use the Ito chain rule or Ito formula. But first we do the product rule for this product of two processes, which gives us the phi double prime evaluated on the process and so forth, times the increment of the q squared, but by chain rule, conventional chain rule, this is 2 times q squared, 2 times q dot, and inserting the ordinary differential equation that the q process is assumed to satisfy, we pick up this minus 2, the 2 was from the chain rule qtb dt, that's the first part. And then comes the second part from the Lightness rule in this case, so the qt guy squared remains unchanged. And then we do a conventional Ito expansion of this combined evaluation there, which involves first a Ito expansion in classical terms, modulo the Martingale increments, which means that we have the first order derivative of the phi double prime function multiplied with the increment of the dxt, but the increment of the dxt modulo Martingale is only the bxt dt, so that's the b guy. And then we have the Ito correction term, which comes with the 1/2, and then it will be the second order derivative of this second order derivative, so it's the fourth order derivative evaluated on xt times the bracket process of the x, but the bracket process of the x is a dt. So that is this part here comes from the classical Ito expansion of this phi process with regards to the inserted process x, and then comes as the second component the derivative of this combined evaluation with respect to this inverted time operation, which produces a minus by chain rule, and then I can insert the PDE, which is solved by this phi double prime function, which is exactly what I do here. And if I compare the terms, then I see that by the choice of the ODE, which was solved by Q, so first of all, I have certain cancellations inside the second part, the exterior bracket here, which are cancellations for the fourth order part, and I have a cancellation regarding the third order part of this, which come in here. And finally, then I compare them there. If you still have this phi second order derivative, which was in the first in the first factor expansion from the Lightness rule, and this will then cancel out with, if we do it properly, with this term here. Not quite, as I just see. So this part here, let me say it again. So this part here cancels. Where do we have the phi second? Right, that's probably it's still correct what I said, but I probably did not invoke the Q differential equation properly, so I just identified a misprint. So here, in fact, we do have a B prime. That's the right formula, because that's coming from the ordinary differential equation, which we were supposing for the Q function. So therefore, here I did not write that properly. Here we have to write a B prime. And in this case, in fact, I do see that this term here cancels with this term over there. So that altogether I have only one component surviving modulo the Martingale relation, which is qt squared b double prime times phi prime at least t minus t. That was the Ito expansion of the first of these two summons. And now I pass to the Ito expansion of the second of these two summons. So again, it's the first Lightness rule, which leaves the first component unchanged, and then I have to pass to the derivative of the R process. And then I have this second part from the Lightness rule, which produces in similar fashion as before. I do this conventional Ito expansion with respect to the x variable inside. This is again modulo Martingale, so therefore the Brownian increment will not show up here. And then I do the time expansion of this phi function. And here I insert again the parabolic PDE, which is solved by the phi prime function. And if I compare again the equation that is solved by the R process, let us have a look at the equation again that is solved by the R process. So the R process brings about an R b prime xs minus q s squared b double prime. That is all met with the phi prime. Let's have a look what we pick up for the R here. So we have the phi prime is wait a second, I'm sorry. correction. So let us check first, probably with a little more care, what we ultimately have found here. So I'm picking out, or I'm writing out this guy again, which is this part, and then I'll try to identify what kind of cancellations I have in the second line here. So what cancellations can I find? I have a cancellation of the third order part, and I have a cancellation of this second order part, these two second order parts, because all this comes with a minus, and hence the second line altogether brings only this expression, which, if I write it out together with what remains from the first line, I pick up a phi prime t minus t r t dot minus phi prime t minus t b prime r t. And if I then combine the two computations that I just did, if I then combine the two computations that I just did, recall the first computation produced a qt squared b double prime phi prime t minus t. So that's a b double prime phi prime t minus t. The phi prime will be present in all of the remaining terms after summing up, so the phi prime goes to the front of this. And then I have the qt squared b double prime, which is the remaining component of the first summand. And then I have the remaining two components of the second summand, which is this here. And hence now I can compare this with the ODE, which I was assuming that the R is satisfying, or which was the defining ODE for R, which tells me that this bracket here is a 0. So in fact, modulo Martingale, a Martingale increment, the n process is just a 0, which means that the n is in fact a local Martingale. Now comes the second Martingale. Okay, I have seen that this n process is a Martingale, and now comes in the k process. My control, I wanted to work with two control processes, k and l. So let us look at the expansion of n product with k. Then by Lightness Rule, since k is supposed to be C1 smooth, it's of bounded variation, so the Lightness Rule is the conventional Lightness Rule. I have two components, therefore, but the increment, or the stochastic interval of k with respect to the increments of n will produce a local Martingale, so therefore that part will not play a role, it will vanish if I really work modulo Martingales. So modulo Martingales, this increment is only n t times k dot t dt, which tells me, of course, that n t times kt as a product of two processes minus this integral is again a local Martingale. The next argument is that the process which is obtained by combining the phi function backward in time with a solution to the stochastic differential equation, if I do this combination, then this produces a Martingale, and or even by Ito expansion, simply we have exactly this representation. That's a straightforward application of Ito formula. We did this already effectively in the last semester when we were talking about stochastic representations of the heat equation and so forth. So, as a consequence of this, I find that the phi prime process, the phi prime function evaluated at t minus s evaluated at xs times rs k dot s minus phi t minus t xt rs k dot s dws. This is again a local Martingale. Well, how does that come about? Well, what we have here is, this one here is by the formula above. This is a local martingale. This component here alone is a local martingale. This component here is also a local martingale. So what we find here is the product of two local martingales, which we evaluate at time t. And we know that if we subtract from the product of two local martingales, the bracket process, then that yields back again a local martingale. And it's a simple exercise to convince yourself that this term here is nothing but the bracket process of this local martingale with this local martingale. That's, again, a consequence, if you like, a direct consequence of this representation of this martingale through the formula above. So let me say that again. This factor here is a local martingale. This factor, since it's a stochastic integral against Brownian motion, is a local martingale. So therefore, we know that the product of two local martingales in general is not a martingale, but if you subtract the bracket process of those two processes, of those two martingales, then you get back a local martingale. And what I'm saying is that this guy here on the left-hand side is nothing but the bracket process. So therefore, also this guy here is a local martingale. The next martingale which we consider is one which appeared already in our discussion of the Bismut derivative formula for the first order derivative. It's the martingale which is obtained by evaluating the phi prime function in reverse time along the trajectories of the process, but multiplied with this factor q to the qt function. And by the computation that was done there, we convince ourselves that this is a martingale, and moreover, we have this explicit representation of this martingale increments by means of this stochastic integral. And hence, if we take this martingale, which we have just introduced, and take its product with the martingale, or the local martingale, which is obtained by integrating the q process with the k dot process against the Brownian increments, then this produces a martingale provided we subtract the bracket of these two martingales, and by a similar consideration as above, by the same argument as above, we see that this integral here is exactly the bracket process of these two martingales over there. So therefore this is a local martingale. And now comes the first important step, or that allows us, or that will bring all these effectively three different martingales together that we have considered so far. Namely, I claim now that the following combination of stochastic processes produces also a local martingale, which is this phi double prime multiplied with the qt squared times kt, and the phi single prime evaluated on xt times rt times kt, minus these products, minus the sums of these two products of these two martingales, which we have just considered. I claim that this is a local martingale. Well, why is this a consequence of what we did before? Well, if we look at this, at these two, the sum of these two parts, this is basically the first part here inside this box is the product of nt and kt, which was appearing somewhere on the page before. We know that nt, kt as a process is a martingale if we subtract this integral. Well, this integral, if we look at it, this integral is an integral where the n process appears, which is a sum of two components. And one of the two components inside the integral, again when integrated against the k dot, is exactly this guy. And that is 0 modulo martingale, or is equal modulo martingale to that component here. So if we are interested only in the preservance of martingale properties, we can replace this guy by this guy. And likewise, in this integral of n against the k dot, there is a second summand that comes from the n operation, which was dealing with the second order derivative, and that's exactly this fellow here. And by the just established martingale property, we can replace modulo martingale, that term, with the product of these two martingales. So that's the only replacement that we do, we do these two replacements for these two integrals which appear in this compensator on that right-hand side, which allows us to conclude that this stochastic process altogether is in fact a local martingale. Okay, this formula here, or the fact that this is a martingale, is almost there where we want to be, because it involves quantities or certain stochastic integrals which involve only first order derivatives, which involve only the second order derivative of that function phi, of which we want to make a statement, and it involves, except for this, it involves the higher order derivatives of phi only in two instances, namely in this part and in this part. If we take a look at this instance of the phi prime, that's not so troubling, in fact, because if we want to evaluate this, for instance, at time little t, then by our definition of the process k, that will have a zero. The r of 0 is defined to be 0, and the k at the time t is defined to be a 0. So therefore, if you evaluate this martingale in the two extreme time points 0 and t, this part here will not play a role. So therefore, the fact that there is a first order derivative here, or a term which involves the first order derivative of the phi function, does not bother us too much. But this part here is a component which has the potential of causing trouble, or appearing in the expectation at time capital T, because we have no factor in front, which is 0 at time capital T. So therefore, you have to find one more argument how to deal with that expression. And this is done in the following form, by introducing effectively this second control process L in the following fashion. We see that this process here, again by what we did before, phi prime t minus t and valued at xt times qt, that is a martingale. And if we take the product of that martingale with a process of bounded variation, that is again a martingale, if we subtract the corresponding compensator according to Lightness Rule, and this compensator according to Lightness Rule is obtained by this formula. So therefore we see that this process here is a martingale. And second, we also know that the process Qs k dot s integrated against the Brownian motion is also a local martingale. The process that we are heading for, or that we take particular interest in, is this component. L here is our second control variable. And now we want to consider the product of these two martingales again. And we know that the product of these two martingales is again a martingale if it is so that the bracket of these two processes vanishes. Well, there's only one stretch at which the bracket of these two processes may contribute, and that's the stretch where the Q process is not constant, It is very good that this process, which we have here, is a martingale, which means that we are already almost there. Why is that a good martingale as an intermediate result? Well, it is a martingale which involves a quantity which we want to evaluate in the end, namely the second order derivative of phi evaluated at some point, multiplied with some processes which we basically can control reasonably. So therefore that's exactly the quantity which we want to make a statement about. And if we add certain quantities, we obtain something which is constant in expectation, and the terms that we add or subtract will involve sometimes higher order derivatives of the function phi and sometimes not. So this term here, for instance, is particularly good because it does not involve higher order derivatives of the function phi. That's a term of the nature which we would like to see in the end. this term here does not cause any trouble at the boundary time points of our time interval, because at time equals 0, R naught is 0, and at time t capital equal to capital T, kt is 0 by assumption. So therefore this term here, the second term in this sum, does not contribute to this process at the two extremal time points t equals 0 or t equals capital T. The only term which might produce additional contributions in the expectation with higher order derivatives of the function phi is this one, because at time t equal to capital T, this stochastic integral is not 0 in general, of course, and we have here a certain contribution. And this contribution involves the first order derivative of phi in contrast to what we want to achieve. Namely, we want to have certain expressions which do not involve any higher order or derivatives of the function phi. This problem of this final term will be dealt with now in a final trick by the same consideration as we did already for the first order derivative formula. We consider the martingale which is generated by the first order derivative of the function phi. That martingale came along with this correction factor qt, and if we multiply this with the control variable, then if we subtract the right stochastic integral from phi, then this produces a martingale. This is a computation that we did already in the lecture for the first order Bismut derivative formula. That's good for any control function L, and if we write if we shift L by a constant, that does not play any role for the local martingale property. The second martingale we want to consider is just this stochastic integral from product of the Q process with the k dot dws. So this is again by construction a local martingale, and we claim now that the product of these two processes, of these two local martingales, is again a local martingale. Why could that be? Because the bracket of these two processes, Z1 and Z2, disappears. Well, we wanted to make the choice of K and L in such a fashion that L is constant 1 on the subinterval from 0 to S, and K is constant to be 0 on the subinterval from S to T. This means for Z1, where the L process appears, that on the time interval from 0 to S, Z1 is constant 0. And on the time interval, on the complementary time interval from S to T, K is equal to 0, which means that K dot, of course, is 0, which means that the process Z is constant there. So therefore, these two martingales, Z1 and Z2, are constant on mutually exclusive time intervals, which means that the bracket process of the two martingales is just 0, and therefore the product of the two martingales, or local martingales, is a local martingale because simply that bracket process vanishes. That's very good news, because if we now take the product of the two, we see that there is, if we take the Z1 and the Z2 product, we see that the product of the first summand of the Z1 with the second summand contains a part. If we factor out this qt, it contains a part which is exactly this product of these two martingales. So if we subtract the Z1, Z2 product, then this martingale here will be cancelled by the corresponding product of the first summand of this first summand product with the second Z2 process. And what we achieve, in fact, is that we pick up, instead of the Q, we pick up the L process in the product. Altogether, this yields the following intermediate result, which I state as a separate lemma. Let phi be a sufficiently smooth function, which is a solution to the parabolic PDE, and let x be a solution to our stochastic differential equation generated by this function b. Let q and r be solutions to these corresponding ordinary differential equations with random coefficients that we consider. Let k and l be two control variables or control processes, which can be deterministic processes, which are chosen in such a fashion that there is an additional intermediate subinterval from 0 to s, such that L is constant 1 on the subinterval from 0 to s, and k equals 0 from the interval from s to t. Then the following process, phi t, is a local martingale, and it is just a collection of these processes which we have just seen. So it's this phi double prime with this combination, it's this guy which we discussed, then it's this other component which is of no harm because it does not involve derivatives of the phi, and finally it's this phi process, and here I guess there is a misprint. Here it's the phi prime process at these correction, no, it's not correct. So it's the phi process which was coming about from, let me see it again, right. So it's this phi process multiplied with this stochastic integral and multiplied with this stochastic integral. That is another term which appeared now in our formula. And finally, it's the phi prime process with a qt and lt and multiplied with the stochastic integral here. So that's a local martingale. That's the statement of the lemma, which we have just established. And as a corollary, if we moreover assume that L of capital T equals K of capital T equals 0, and phi is this solution, then we ultimately obtain this representation, which is basically the main step for this Bismut derivative formula. We find that the second derivative of phi at time t evaluated in position x equals this expectation, which is now a sum of two expectations. In fact, it involves the evaluation of the phi function at these position of the process at time t, and these twice, and it involves either the stochastic integral of r with k dot, or it involves the product of the stochastic integrals of L dot and K dot with the Q function. So that's the derivative formula for the second derivative in this style, and we see in fact that in this representation the derivative of the function phi does not show up in this formula on the right hand side. Okay, the proof of that is now easy. Namely, we just check what the phi, this capital phi process of the previous assertion, what does it look like at these two extreme points? Well, by the choice that L and K at terminal time are 0, we find that this part here, which is this second, which involves this first order derivative of phi, does not contribute at time capital T, and the only part that actually does contribute, also by definition also K here, that guy does not contribute at terminal time. And moreover, at terminal time we have only these collection of stochastic integrals effectively which show up. That's exactly the statement here. So at terminal time we only have these terms which involve the stochastic integrals, and at time time t equals 0, all these stochastic integrals do not contribute because the stochastic integral by definition starts at 0, and by definition of the R process, since we defined it as a solution for a certain ODE starting at 0 at initial time, R at 0 is 0, so therefore this term does also not contribute at initial time, and we see that we have to evaluate this expression only at time t equals 0, but again by our definition of k being equal 1 at 0 and q starting from 0, we have exactly that phi of naught is the deterministic expression phi double prime t at the starting point. And hence, since we wanted to assume that phi here is a bounded function including all its derivatives and so which appear here, we can equate the two different expected values, where the expected value for time little t equals 0 is not really an expectation but just an deterministic value, namely phi prime of t, and the expectation of this phi process at capital time is the expectation of these random quantities which appear in this representation formula. Okay, from this representation formula, we can basically proceed systematically, as we did in the previous case of the first order derivative, to map this property from abstract solutions to this particular parabolic PDE to solutions or to the action of the semigroup on an arbitrary function, which is continuous and vanishes at infinity by the same trick. We convince ourselves that the operation of the function to this of the operation of the semigroup to a smoothened version of this function is smooth enough in order to apply this previous argument. Then we find this explicit representation for the derivative of this, for the second derivative of this smoothened function, and then we let the regularization parameter tend to 0 in order to convince ourselves that this kind of representation formula is true. So this argument will give us exactly the precise representation formula that was given at the beginning of this session of today. That will be the formula that we will obtain. And of course, as a consequence, we can see that this operation of the heat semigroup, or the semigroup induced from the solutions of this stochastic differential equations, produces a function which is twice continuously differentiable with first and second order differential, being functions which vanish at infinity. So in particular, we have not only established the Bismut derivative formula of first and second order for the action of the semigroup, but we have also shown that the operation and also the resolvent operation maps into this space of a continuous function which vanishes in infinity, which by the argument that we indicated produces in fact that these C02 functions are in the correction, that the domain is in fact exactly these C2 functions which vanish at infinity together with its first and second order derivatives. This completes this long and technically involved excursion into the possibility to represent the regularity of, in this case, parabolic linear PDE by means of stochastic differential equations. I wanted to present this segment because, first of all, it is some kind of device that people use today actively in research, in particular in the context of studying stochastic processes which assume values in non-Euclidean, for instance, in Riemannian spaces and so forth. It is used in infinite dimensional situations for the analysis of stochastic partial differential equations, and hence it's a very powerful tool. And if you want to have a full-blown extension of this technique to the case of Brownian motions or stochastic differential equations on Riemannian manifolds, I recommend a recent paper where basically the computations here for the second order derivative formula were taken from, in a simplified version, of course. So the full-blown multidimensional computation in a curved state space situation are done in this paper of James Thomson, a young researcher who is currently at the University of Luxembourg. And the paper that I recommend for reading is his paper, which is called Derivatives of Feynman-Katz semigroups, which is much more general than what we presented here today. From this lecture on, I will try to make the step towards real applications in physics, and that will be probably the remaining program of our course in this semester.